two more important terms, just more terminology on stuff you've just seen though, is an extensional fault. All this refers to is a fault where the bedding layers are extending, there's tension, there are normal faults. So the overall effect is now that region is longer. A contractional fault, there's shortening, contraction. This means there are reverse faults. The overall effect is that the area is now shorter. So now we know how to talk about it. How do we draw it? Drawing 3D block diagrams takes practice and artistic skill and doesn't work on a map. It only works on a little 3D block that you draw. On a map, if we have a normal fault, we have a couple of choices. We can have the little bars. You can have little bars with balls on the end, or we can just label it with a U and a D for up and down. All three of these are showing the right-hand side dropping down, which means the right-hand side is our hanging wall, moved down relative to the foot wall. And one easy way to think this is if you've got, you tie off a little string with a ball on it, put it at the top of the hill where the fault block has gone down. That ball and string are hanging down that fault plane. So they're down towards the foot wall, or running down the foot wall towards the hanging wall that dropped. On the other hand, if we have a reverse or thrust fault where the hanging wall has moved up, we're going to use little triangles. The triangles go on the hanging wall, which is important because if you draw them backwards, it looks like you have the fault going in the opposite direction. So the little triangle flags are always on the hanging wall. They do not point in the direction of motion. When we want to give sense of motion, we use these little arrows that only have a half of a point on them. So you can see it down here in the cross-section view with a reverse fault that has had part of it eroded away in the middle. And you can see it on the strike-slip fault. So across the top is all map view, bird's eye view, satellite view, looking down. Only this one little part labeled cross-section is a side view. Block diagrams are extremely useful for looking at something and picturing it in 3 dimensions and giving a good sense of where things used to be if you know where they are currently. Like we can see the hanging wall, and we can see the little gray bed in there, and we can see that, hey, it used to be up there and it has moved downward. The little arrows, of course, help add that sense of motion. But another symbol that we can use in a block diagram is this little circle and circle with an X in it. They give the in of the page, out of the page motion. Anytime it's the circle with an X, it's moving backwards into the screen or into the page, and the circle with a dot is moving out of the page. In some exercises that we do with fault symbols, you'll see these in the side view. When we're doing a map view, we never use the circle and the circle with the X. That's only for cross-section or block diagram view. In the real world, it's not nice, perfect little blocks. Erosion runs rampant all over the earth. It changes things. It makes things pretty, but difficult to identify until you get practice. Now, because the erosion is going to go on and it doesn't say, oh, here's a fault block, I can't erode it, it does things like leaves sections behind or erodes through them. So these four terms will get seen a lot. A lockathon is a rock that is moved. So that hanging wall that gets thrust up over something is an allocathon. An autocathon is a rock that's still where it was originally. It did not move. So that bedrock that was sitting there, it's the footwall, it's still there, that's an autochthon. If in that hanging wall that gets thrust up over the other rock, and it sits there for millions of years and some erosion carves a hole in it until you can see that rock underneath, we call that a window. It's like a window through the rock to the ground underneath, also called a fenster. So a fenster is the same as a window. On the other hand, sometimes some of that footwall gets all the rock around it eroded, but it sticks around. So you have a piece of that footwall that's not touching any other footwall. It didn't, slide further away. It wasn't moving fast enough to do something like that. It was part of it, then the erosion happened, and now it's just stuck there. It's called a clippe. So it's an isolated portion of that hanging wall that's now surrounded by footwall. So here's a really cool, nice chunk of rock. Gorgeous structure. What would we call this structure? It's right here. It's a clippa. This was part of a huge thrust fault where the hanging wall covered this whole area. Then over millions of years, almost all of that hanging wall has eroded away, leaving only this chunk. So how about this one? Well, clearly some kind of a basin-like structure, but more specifically, this is a window or a fenster. So up around the top here, we have a hanging wall that was thrust up over this rock down here in the middle, which is part of the footwall, which we can now see through the window in that hanging wall.